Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning. It is my pleasure to introduce today to you David Chafness on this sort of beautiful Seattle summer day. David was just finished his PhD at Northwestern University, and he's interested in networking and distributed systems and measurement. And he's actually, what I like about his work is he's built some really large-scale systems out there. Some of the sort of systems he's built, sort of were adopted by more than 1 million people, which is pretty impressive for a research project. And sort of, so he's going to tell us a little bit more about it. And welcome to Microsoft Research.
All right. Thank you very much for the introduction. So today I'm going to talk about crowdsourcing service-level network event detection. This is work done as part of my PhD at Northwestern. Just for the record, I'm starting a postdoc at University of Washington with Tom Anderson next month. But this work was done at Northwestern with my advisor, Fabian Bustamante. And the motivation for this work is that internet activity is increasingly driven by services. So these include things like video streaming, online multiplayer games, downloads, voice over IP. And when you're in this domain, we're finding increasingly that network performance is essential to the success of how we use the internet. And increasingly, user experience is the key benchmark here. So if users are unhappy with the performance they're getting, then everyone loses. So in the case when these are due to network problems, network providers lose because the service providers are mad at them, users are unhappy, and then the service providers themselves can lose revenue and reputation. So it's important to actually detect these things and figure out when they're happening so you can solve them as quickly as possible. The thing, though, is that network events are pretty common in the internet. And when I say event, you're going to hear this throughout the talk. What I mean is really a general view of any change in network status. So some of these can actually impact customers, some of them don't. And I'll specify a little later what we're focusing on in this work. But another way to classify events is those that are well understood and those aren't. So the kinds that are well understood, planned maintenance, operators usually can plan around them before they happen. There's also unexpected events, but they're still well understood, such as fiber cuts. And again, there's usually some kind of redundant infrastructure in place so that they can take care of that easily. And then there's internal peering changes. So in this case, operators will change their routing configurations. And again, usually they know what's going to happen. But then there's these other kinds of problems that are harder to detect and diagnose. These include so-called silent failures. They're silent in the sense that users, their customers, will actually see them, but the operators themselves aren't aware that they're happening until they get phone calls with complaints. There's other reasons that things could happen. Operator misconfiguration. Routers themselves have software that can have bugs and impact network traffic.
Do you consider sudden extreme changes in load to be an event or not?
I do, and as I'll say later, what we actually focus on is detecting problems that affect end-to-end performance for users. So if there's a sudden change in load that actually changes the way that users experience a piece of network software, then that's something that we'll look for. But that would be an event. So and that falls under the category of change in network status. And then there's things that operators can't control, like external peering changes. For example, there's a case with a large ISP that was connected to Comcast, and they changed where they peered with that ISP, which changed the way that their content distribution network gave performance to their customers. And these are tricky problems to figure out. Okay, so in general, there's been a lot of work on detecting network problems. At a high level, you have a bunch of signals. These could be anything from throughput or flow summaries, like for the kinds of problems that you described. They also include summaries of routing updates or even just simple active probes, such as figuring out packet loss or round-trip times along links. And then you run a detection algorithm. There's a lot of different ways you can do that. And finally, once you've actually detected a problem, the last step is to actually isolate the event so that you can fix it. So that's at a high level. And as I said before, this work focuses on problems that actually impact end-to-end performance. So specifically, if users can't see a problem in terms of how it impacts their applications, then it's something that we don't focus on in this work. In this domain, what we would like to know, obviously, is what is the service level view? What are applications seeing in terms of their performance? And what we really want is a system that can do in real time or online analysis to figure out what problems are happening in the network. If you do an offline analysis the next day, it doesn't really help you fix the problem that's happening right now. And we also want a system that can scale with the number not with the number of users in the network, because this could be millions or billions of users. We want something that scales with the number of events that impact performance, which, although events happen all the time, is typically smaller than the number of users. Okay, so what are people doing right now to detect these problems? ISPs are constantly monitoring their own networks. This is actually a screen capture of AT&T's Global Network Operations Center, which is pretty cool, with their football-sized screen with the status of the network. So that's, I mean, like up here, what you see is they're monitoring RTTs across their global network. And so they can see these aggregate views. They have a high-level summary of their network, but it doesn't really scale to the very edges of their network. They're not sending probes out to your routers at home, for example. So they can't, there's large parts of the network that they can't see. And what they see is something like an aggregate, like round-trip time or packet loss, which doesn't really tell you, is this impacting performance for my video streaming or my file downloads? Another approach is looking at BGP feeds. If the routing is messed up, then usually there's going to be a problem with network performance. So these are really good tools, but again, they only are useful in the places where you can see the routes. And BGP is, of course, an information hiding protocol. So as a result, there's actually a limited view into the network. And then last, there's active probing to simulate what applications would see. This can really give you the view that you want to see, but the downside is that there's overhead involved that scales with the number of endpoints that you monitor. And then there's your visibility into the edge of the network is limited by where you have your vantage points, where you can probe to.
So you've actually seen this place?
Gina?
Yeah.
Yeah, this is, go ahead.
So you have this visual, thing about all the RTT, etc. But I'm assuming there are some alerts that are raised that cause the operator to go and look at some historical thing, what's happening in the analysis. Or is it that the system actually does the analysis and then provides it to the operator? And what is the use of the visual?
As I understand it, so they do have alerts, that's for sure. And since I signed the form that says this is recorded, there's probably certain things I can't say in terms of what they actually do. But they do have alerts. I can also tell you at a high level that any system that has alerts also has false alarms and has certain sensitivity, especially if it's threshold based. So they're useful for sure. They see a lot of big problems, but like any system in that domain, there's limitations in terms of how much of their network they can see and granularity in terms of time.
Yeah. And one of the problems we've had, you probably have encountered this too as well, is that there's this term C over edge, right? So you see so many alerts that the operator starts ignoring it because you don't know which alert is actually important and which is not.
Exactly, and that's something I'll cover later in the talk. For our system, you never want to have a system that generates so many alarms that it becomes annoying or overwhelming. Excellent point. So our approach, we see it as an alternative approach to the existing monitoring tools. And what we want to do is actually push monitoring to the end systems themselves, where the problems that we're trying to detect are occurring. And the high-level idea for this system that we built is you've come up with a definition of what a problem with performance is for an application, and you look for it locally at each host. And if enough hosts see the same problem at the same time in the same network, it's likely to be a problem with the network. And throughout the rest of this talk, I'll formalize how we actually detect problems using this approach. So before I go into those details, I just want to talk about a couple of advantages. One is, obviously, when we're running on end systems, we see exactly what the user sees. And this is something that's difficult to do from a centralized location. There's also no need to deploy any additional hardware or get access to proprietary ISP information. And this means that you can actually run this anywhere. As an end system solution, any number of hosts can run this. And in that sense, if any host can install the software, then it can grow naturally with the internet if you give users a reason to install it. And lastly, by running inside the applications, you can actually you can possibly run inside an application itself and use the information at the application layer to distinguish normal events from abnormal ones, or normal changes in performance from abnormal ones. So an example that I'll keep coming back to is in BitTorrent, when you finish downloading a file, your download rate drops to 0, but your upload rate continues. From the outside, you see a sudden drop in download performance. It could be a problem. But when you're inside the application, you know that's normal behavior.
Just to be clear, you actually talked about changing the applications?
That is one path. So what we're able to do is use an extension so it doesn't actually change the application. You build on top of it and get access to it, get access to application information through a public interface. To get the application-specific information, you do.
I was thinking more generically.
Right. So it's possible to run our approach at, for example, the operating system level, in which case you need to get access to that privileged information. So it's.
But there you may not need access to. I mean, the application generally will provide some information, some counters, some logs or whatever. Mm-hmm. And you might even sort of be tracking some packet flow from the application, but that doesn't mean the application has to change. You don't have to rewrite the application, you don't have to change the behavior or anything. You're just observing what the I/O is, and from there you're bootstrapping. So that's a distinction I wanted to sort of understand. So do you actually work at that level, or do you actually go and probe the application and say, hey, what is happening, tell me, then determine what the trigger is to say if it's a problem?
So in our prototype, we monitor network level statistics such as aggregate throughput and per connection throughput. And that's information you don't need to be at the application layer to get. So you could run that at a lower layer. But to distinguish those events that are normal from those that aren't, we do need application level information in this prototype, which is BitTorrent based.
Well, that doesn't seem necessarily true that you would require it, right? Because you could still, for example, train over a network data corresponding to that program. I mean, as long as you essentially had someone saying, what corresponds to what events in the training data in the real program, right? Then you could still just look at the...
Definitely. And so I don't know if I just used the word require, but it's not required. It's that the more information you have, the better the system can work. The main issue is that the more reliable your detection is at each host for what is actually a problem, could be a problem with the network as opposed to being due just to how the application runs, the better you can detect network problems together through this crowdsourcing approach. So yeah, it's at a high level, we just want to come up with a way to crowdsource it and come up with reliable inferences based on a collection of locally gathered information. And then any additional information you can add at the local detection phase makes it that much better.
You're saying it is still usable, even for any normal application, your system would still be usable?
It'd be usable, and so it's an open question though. So we've done a prototype in BitTorrent and shown that it works there at the application level. We have not been able to experiment large scale with things like video streaming or VoIP or other applications, and that's something that we'd like to see how far this goes. Going at the operating system level also gives you the additional advantage of gain access to all the flows on the machine. So that's another issue, is that if there's applications interfering with each other, you pretty much need to be at the OS level to get that. And we don't, the prototype doesn't do that. We're still able to detect problems even with that limitation. But again, in this theme of adding more information makes it better, this would be definitely something that having a service that runs at the OS layer that gives access to this kind of information would make this tool more effective.
Not to belabor the point, I think that it does get more difficult in the OS level because the OS is, in some sense, is stateless. It doesn't really know whether the application is okay with what, and because the application may have some other thing going on which might cause sort of some delays to happen, right? So I mean, but the notion of aggregating over multiple points and seeing if everybody else is sort of having the same behavior sort of seems unusual. That might be the trigger mechanism to start with anomaly detection there.
Right, and just to step back, at the OS level, you still do need to be able to identify what is a problem. So if an application's view of performance isn't something that you can capture through those aggregate sets, then you're right, that won't work. It happens to be, in the case of BitTorrent, which is the example I'll use here, throughput is enough to be a trigger for that.
I just wanted to mention that the other thing that looking over this list of advantages that you sort of didn't mention, I think to me it seems like a big deal, is that doing it at the OS level requires, in the case of Linux, root privileges. In the case of Windows, your screen basically goes dark and you say, do you really want to run this? That raises the barrier of adoption substantially over saying, just install this BitTorrent plugin, don't worry about it.
Yeah, and that's,
yeah.
I guess the list was already long enough, and there's the proprietary ISP information.
But the disadvantage is that you got to do it on a per application basis now.
Yeah, absolutely.
As opposed to you sort of do it in the OS and then start to look at OS.
But it helps with coverage. If you can avoid privileged operations, it's easier for users to install and less of a barrier to adoption.
What I found before is like, even if you go to networking researchers and tell them, well, just install this and run it as root on your machine, to your friends, they go, I'm not so sure I want to run it.
This is a research software and run it as root.
Apply it in your browser or in your BitTorrent. Sure, I'll do it. Big deal.
All right. All right, so we've talked about some of the advantages. There's, of course, challenges as well here. And these first two challenges are general to any end system monitoring approach, any monitoring approach. Scalability is one of them. If you want to truly cover the whole internet with your monitoring, this could mean potentially millions or more hosts, and centralizing this data collection or data processing requires substantial resources that not everyone has access to. There's another issue here, which I mentioned before, is granularity. So you want to not only detect events quickly, you also want to be able to isolate them. So there's two aspects of granularity, and so these are general things that you want out of a detection system. Once you move to the edge, there's a host of new challenges. Some of the key ones, privacy. Obviously, users don't want their private data shared. As we show in this work, just monitoring performance locally at each host and publishing summaries of whether there's a problem or not avoid sharing any personal information. There's trust. So, and this is from the perspective of the detection algorithm. These are uncontrolled hosts. They could give you potentially bad information, and you want a system that's resilient to that. And last is the adoption issue. If you're going to crowdsource event detection, well, you need a crowd. Yep.
Is there also a problem in which serious network malfunctions will cause none of the information actually sent from the system to get through, or not enough to actually detect a spike?
Yeah, so I think what you're talking about is something like a disruption to the extent that there's just partition of the network or something like that.
To the extent, right? I mean, it could be that you're getting information from some of the nodes, but not a lot, so it doesn't really look like maybe in the most severe cases, things actually sort of look normal as far as the system is concerned, because you just get a small. No. But I guess in that case, those type of events are probably easier to detect anyway.
It very much depends, and it depends on what's happening. It depends. So if some of them are reporting that there's a problem with the network, you do need some minimum number, or be able to come up with some confidence that there's actually a network problem happening. So there's always going to be limitations, and even in the case of a partition, well, I mean, there's not much that hosts can do to communicate problems with each other.
That kind of thing must be easy to detect.
Those are usually some of the bigger problems, and we're not saying like, well, I mean, sure, we have hosts that actually will republish their information periodically over the course of an hour, say, so that at least there's a record of the event happening, assuming that something that big gets fixed that quickly. But yeah, we're not targeting disruptions as the thing that we can do better than others. But there's the example I'll show you. Performance got very, very bad in a network, but it wasn't a disruption, and we were still able to get enough data to make these conclusions. Okay. All right. So for the rest of the talk, I'm going to actually go into the details of our approach for crowdsourcing event monitoring. And then I'll present a case study using BitTorrent in the BT Yahoo network in England during one of their big disruptions. And then I'll present results from a wider area evaluation. This has been implemented as a BitTorrent extension called News for Network Early Warning System. And I'll also talk a little bit about how we're trying to crowdsource event labeling through a public interface to the events that we detect. And we call this News Site. And finally, I'll conclude. All right, so the high-level architectural diagram of how we crowdsource event monitoring is that you have a distributed system with a bunch of hosts connected in this internet cloud. And each one of these has a light blue box, which is blown up at the top. So each host has access to performance signals. These could be throughput, latency, any number of measures. And each host does local event detection. So generally, each host is passively monitoring these performance signals. By using passive monitoring, you avoid the overhead of active measurement that could become an issue as you scale out the system. And these could be general network-level metrics such as throughput. These could also be application-specific, such as content availability in BitTorrent to help you distinguish what is expected application behavior. And so local detection is focused on detecting drops in performance. You do have to define what is a performance problem. Once you do, each host can identify that it happens by sampling periodically, and then use its any other additional performance signals that it has to distinguish when those events are expected or not. And to avoid this large overhead of publishing all of the data that each host sees, instead, all they do is publish potential local problems. Well, they are local problems. It could just be your router, or it could be a wider area problem. But we're going to start by having each host just publish information about local events. So these go out to some distributed store. We assume that the system has access to a distributed store. And then after a host detects a local problem, the next question is it just me, or are other people in the same network seeing a problem?
I'm not clear. Like, what precisely is supposed to do?
So I think that there's a slide on this later in the talk, but I'll give you an example in our prototype. So you have a detection algorithm and some settings that you use on that. That's part of what's posted. The timestamp and the host network so that you can isolate where the event occurred. In network, you can have different levels of granularity posted in these events. The timestamp is, they use NTP to synchronize clocks so that they're relatively close to each other in time. And then has to be an identifier that distinguishes events from different hosts so that they can, when they read from the distributed store, they can compare these events. And then there's the information we use for actually doing the analysis, a probability analysis, to see if it's likely to be due to the network or not. So they also publish the rate at which they're seeing local problems. And that's key input, as I'll show later, to the probability analysis. So I think in our implementation, it's around 40 bytes per report. That's
Even coordinate across time then, right? Because every application could be in a different state of time when something happens. So they might all see different events per se, right? Or they may see different problem without knowing it's the underlying problem the same, but
are you talking about like it may affect them at slightly different times or within a region? So the implementation sort of comes up with time buckets or time windows. Given an event that you see, you look for any other host events that occur within a window of time, something like 5 minutes.
I guess the issue is that the interpretation of the meaning of that event depends on the state of the application.
that's right, yeah.
Oh, okay. So
So there could be two separate events that you label them separate because the application is in different states, but they actually could be due to the same underlying network problem. No? So for example, if you see a drop in throughput, you see it, let's say, at 2 hosts, okay? One of the hosts actually is just terminating the BitTorrent download. You might say, that drop in throughput makes sense because I'm just finishing my file download, so it's not really a drop in throughput. Whereas the other one says, no, it is a drop in throughput because I'm in the middle of download and I can't download anymore.
So it's sort of a false negative in this case, is what you're getting at.
It sounded like you said that the interpretation of the event depends on the state of the application.
And it does, yeah.
So
locally. So in that case where the application said that this is normal behavior, an event would not be published.
Okay.
Now, if there actually was a problem and it happened to be a coincidence that the client closed their application at the time the event happened, then that's sort of a false negative. And we do rely on enough hosts not doing that at the same time that the real event is revealed. But that's a limitation of just about any approach, that if you don't have enough vantage points up at the right time, then behaving in the course of their actually using the application
that's
normally.
The same thing, but slightly different way. That let's say all the applications are having problems, but they're all in different states. So the event, so I don't actually understand what is the meaning of the event, what is the semantic meaning of the event, but they all say I have a problem at this time, and that problem could resolve, or there's the same problem, but the cause is the same, but the effect is different because they're in different state. So then you're just hearing that the problem is happening at this time. So that's why I was asking, do you actually just look at this time bucket and then say, a lot of people are having problems. I don't know what exactly it is, and then you go, is that?
It's at a high level. It's a system to notify users that there's a problem and operators. It's more like revealing cases where there's reason for further investigation, or there's likely a reason for it. So in terms of actually identifying the root cause, that would be the next step, which is not part of this work, but is a clear follow-up, is to do more isolation. And so this work focuses on pushing the passive monitoring to the extreme. And at that level, you can identify that there's a problem and isolate it to a certain network region. And then the follow-up work would be, you could possibly do limited active probing with hosts seeing the same problem to further diagnose it and do that root cause analysis. But we're just focusing on the first part.
The question is, are the events application specific? Do you need to have domain knowledge of the application to understand the event? Or could you have two different applications having a problem at the same time? This is similar to having the same application in different states. But could you have two different applications reporting events at the same time? And would those events look different, or could...
Well, it's a great question, and it's an open question in this work. We focus on one application as our prototype, and I think that there are opportunities for, say you're running BitTorrent and you're also browsing the web, and maybe there's a problem with CDN and there's a problem with BitTorrent at the same time. And the question is are those two problems the same because there was a network problem, or is it that BitTorrent has some problem, like you didn't have enough seeds, or in the CDN, there's a problem with the CDN service itself. How do these two pieces of information actually correlate with each other? So that's an open question. I think with bulk data transfer, like in the same class of applications, you can use those together. If it's something like a performance problem with VoIP and a performance problem with BitTorrent, those are different applications that require different kinds of performance that may not necessarily, it may not be as easy to put that information together. But that, I mean, it's a great question. As this is designed, each application would be detecting problems separately, and if you had multiple applications using the service, they would corroborate on a per application basis. But I think it's a great question, but we don't have any data to even work with to work towards this problem.
And what's the distributed storage that you're talking about?
So in this sense, we're using. It can be general. It could be that if a company producing a piece of software that wants to use this approach, they can host storage. It could be in a cloud or something like that. In our prototype, BitTorrent has a built-in DHT, so we use that. It's something that removes any dependencies on centralized infrastructure, which is something we wanted to do. Additionally, if there is a disruption that causes a partition, if it's a big enough partition, like think of the Mediterranean cable disruption, there may actually be enough resiliency that the host can communicate with each other at the time. I mean, this is something that Mediterranean cable disruption everyone could see, but you do want something with some amount of resiliency so that the distributed store stays available so that these events can be shared. Okay. All right, so briefly to go over group corroboration. Each host gets access to this local event information. They then identify these synchronous problems that are unlikely to occur by chance, and we do this using likelihood ratio that I'll go into more detail later. And an advantage to this approach is that end users can identify network problems through this software, which allows them to keep tabs on their ISPs. And this is one way to incentivize users to install software. In our deployment model, users have to install something extra. So that's our incentive model. But then any third party can get access to this information by tapping into the distributed store. And users can't fix the network problems themselves. So what we really want is to make sure that operators who can actually do something with this information get that information. OK, so that's the high level.
I often wonder, in Windows, for example, will tell you there's a problem, but okay, so what? What should I do?
Right, yeah.
It's like, anyway.
OK, so then there's the tap on distributed store, and an ISP operator could get access to that same information. And in our prototype, we actually have something that crawls the DHT and makes this information available publicly. OK, so let's say you buy into the idea of crowdsourcing. Where's the beef? How do we actually show that this participatory monitoring can work? Well, you need several things. You need a large-scale adoption. You need active users and distributed storage. These are all fairly big challenges. And another issue is that in our environment, we are pushing monitoring to the edge of the network. And getting traces from the edge of the network is pretty hard. So to solve the first problem, we think that P2P applications are a natural fit for our prototype. So they're used worldwide, generate lots of traffic. And when they're generating traffic, they're implicitly measuring the network. This is ideal for our situation. BitTorrent is one of the most popular P2P applications and has several nice features, like a very popular client that has a plugin feature, so it's extendable, and also has a built-in distributed hash table so that we can get our distributed storage for free. In terms of edge traces, we address this issue in this work using the ONO dataset. And ONO is a piece of software that we put out there, also an extension to BitTorrent, but a different project. And it's been collecting data from users with their permission. It's been installed now just a little more than 1 million times. And so we have trace data from hundreds of thousands of users. And we put this to use to evaluate how our approach would work in the wild.
What sort of data is it collecting?
So it's network level information, such as per connection and aggregate throughput. It also records content availability, records let's see, what else? Number of seeders, number of leechers. Basically the state of the BitTorrent. Everything except what they're downloading. Nothing that would, as we say, as a user of BitTorrent myself, of course only for Linux distros, we don't want to collect anything that could come back and harm the users. We're interested in the network statistics, and these were originally collected for evaluating ONO to show that it worked. And we found a number of other uses for it. One is this project.
Does it actively probe the network, or just passively watch and then collect those data?
There's limited active probes, so we do have pings and trace routes. So we had a recent AS topology study that was based on the trace route data. And those trace routes are actually for the purpose of evaluating the paths that are selected by ONO, the connections, paths over the connections. But they're incredibly useful for a number of other applications. And while I'm here, I guess I can make the plug. This data we're making publicly available. The dataset, the 2-week dataset used for the ONO study has been available. They're anonymized, either at the AS level or prefix preserving anonymization. And we just finally got hardware in place to start anonymizing the whole rest of the dataset. So that will be coming. And there's a CADA-style agreement if you want access to the data, but this is something we want to make available to the community. There's obviously a lot of great stuff that you can do with this. All right, so that's my little data plug. In terms of our coverage, the nice thing about BitTorrent is it's used all over the world, and so is our software. So this is darker colors on this map represent more users in each country. This is actually the number of IP addresses that we've seen in each country. So this was as of a couple months ago, 231K IP addresses in the US. Germany, for some reason, is our heaviest hitter. They have over 500,000. And you get decent numbers in other countries like Argentina, my advisor's home country, 35K. The Sudan, we've seen just over 1,000 IP addresses. So you really do get a view of users all over the world. So it seems like a pretty good way to evaluate an internet-wide monitoring system. And in the next part of the talk, I'm going to focus on a case study and evaluate how well this approach works using BitTorrent as the host application. Specifically, I'll focus on the BT Yahoo network and a specific event. And the reason we focus on them is they are one of the few websites that actually provide information about confirmed network problems. Most ISPs don't want to make this public. In fact, there'll be other results that I can't say who it came from because this is how it works. You can only work under NDAs or find these limited public interfaces. So this is one of those that has public information. And there's an event that happened on the 27th of April last year. They say they're aware of some network problem and they're going to fix it as soon as they can. This is the standard jargon. And you can see there's a time when it starts and a time when it ended. But I just want to point out a couple things before I move on. One, they say, we're aware of a network problem. And then there's the time it started. Well, what this really means is that enough users finally complained at this time that they opened a ticket, and there was some time between that and when it actually got posted. So 3:54 p.m., when you look at the performance graphs, you'll see it doesn't exactly align. But this is typical. And there's another case of this. They say it's resolved at 8:50 p.m. Well, at that point, they're pretty sure they fixed the problem. They actually, according to our analysis, fixed it much earlier, but that's when they actually said that it was done. So this is common. I just want to point that out before I go into the graphs. Okay, so what did we see? Well, when we want to do local detection, and we're doing this in BitTorrent, there's some issues. We're monitoring transfer rates, and we're monitoring this torrent availability and all kinds of other nice information. But these individual signals are actually hard to work with. They're noisy. Here you see actually upload rates on the y-axis, and each one of these different shapes represents a different host that's online during the time of this event. So you see there's a lot of noise in this graph. Each host, you can't control them, so they're not necessarily online during the whole time. You have to work with what they give you. And then they take on this wide range of values. So you can sort of make out from this graph, well, there's some hosts that get about 50K per second. Some of them hover closer around 30K. And this isn't uncommon. Different, even with Comcast or whatever your provider is, you can subscribe to different levels of service in terms of throughput. So you can't just, if you were to just aggregate this all together, you'd get a mess.
So what's the meaning of the different shapes?
Different hosts in the same network. So this is,
Different hosts in the same network?
Yeah, so these are the hosts in the network affected by the problem.
Triangles, another network?
No, it's a square and triangle is a different host, but in the same network. So these are...
You mean the same network as like...
As the event that
height
happened.
is the same? That they connect to?
In this example, it's the BGP prefix is the same, and it's the same as it's BT Yahoo's, one of their prefixes.
All square hosts share a BGP prefix?
No, all square... Sorry. Each square is... So this is a host, and this is another host. Different BitTorrent users.
Why is one square and one is circle?
Just to distinguish different hosts, data from different hosts. So this is if you were to look at, just plot a graph of the throughput for each host in the same network, this is the scatter plot of all those different hosts. It'll become clear once I show you the line graphs. It's just, this is to show you that it's a mess, which it is. It's clearly impossible for you to tell what's going on. But it is a collection of hosts. There's about 10 of them, I think, here, in the same BGP prefix, and it's the one affected by this problem.
You mean a subnet prefix, right?
Exactly.
So do you have information about individual nodes there? Or?
Mm-hmm. We do. We have per host traces, and that's part of the ONO data set. Okay, so our approach to detect problems in this case, if you have per host throughput signals, is that a sudden drop in performance, a sudden drop in throughput is a performance problem, possibly indicating a network issue. So in this case, we use a moving average. It's a pretty simple technique, which is something you want if it's running on N hosts. It doesn't require communication with other hosts. Each host just monitors their own performance, looks for a certain drop, monitors the performance over a window. If the performance drops below a certain threshold, then they say that there's a local problem. There are still open questions that I'll get into later as to what is the right window size and what's the right threshold deviation from the mean to detect a local problem. But the nice thing about moving averages is that these things are fairly well understood, and it's very simple to configure. Okay, so
I guess that answers the question I had, but I was worried about you taking into account, that every node is connected to a network, a pipe, which may be different from the other, and so you do see different numbers. But since you do this, the local analysis, you actually want to normalize for that.
exactly, and that's one of the key things that basically requires local analysis. Even if you aggregated all this information, if you didn't know what each host's notion of local performance was, normal local performance, then you're kind of lost. So what I've done now is taken that mess from before and separated it into two groups of hosts. Here, each color is a different host, and it's their throughput signal. And the reason I group them this way is that you can see visually they experience slightly different events, but they seem to see similar things. So in the top graph, we see definitely something's going on around 1054, and this is before the reported event. There's another group of hosts that seem mostly fine beforehand, and then see an event at, in this case, around 2:50 in the afternoon. So this seems to be when finally they got a clue at BT Yahoo and said that there's a problem. And then you can see that both groups of hosts recover around 5:30 in the afternoon. So moving out, and this is done to show you these graphs where you can visually see the problem. That was using a moving average smoothing. So it gives you some hint that moving averages can actually help us see these problems. Okay, so given that you can detect something locally now, in BitTorrent, how are we going to determine whether each locally detected problem is actually a more widespread one? And there's, when we do this analysis, we have to account for why a group of hosts would see a problem at the same time. One reason could be simply that it's a service-specific problem. So in the case of BitTorrent, if all of those hosts are connected to the same torrent, there was only one seeder, that seeder drops out, well, that's not the network. In that case, it's BitTorrent. In the case of other services, for example, like a content distribution network, similar things could happen if there's a problem with the CDN and it's not actually the network. So we account for service-specific problems. The next thing is if a bunch of hosts see a problem, it could just be coincidence. They're all seeing that you have a somewhat noisy local detection. No local detection is going to be perfect. And there is some probability that it's by coincidence. And then, of course, the last reason is it's actually isolated to one or more network regions. OK, so we account for the first one using the application level information. As I've mentioned this over and over again, in BitTorrent, you can look at the download state to tell these things. You can also see who's connected to who, and hosts that are connected to the same torrent probably shouldn't corroborate each other's events. So this is something else they can do. You can estimate the chance of coincidence by monitoring each host's event detection rate, which gives you an estimate of the probability that they detect a problem at any given moment. And then you use that to determine this union probability, which is the likelihood of coincidence. And the last step to actually tell if this is due to a network or not, we assume that the network grouping is what we're looking for. So we group hosts, look at their union probability, and see empirically what's the rate at which they're detecting these group-wide events. And we take a likelihood ratio to see if these detection settings are actually revealing likely network problems. OK, so to do the union probability, the assumption is that hosts are seeing problems by coincidence and independently. So you may have seen this formula before. This tells you, this is just a standard probabilistic equation that says the probability of any one host seeing a problem given a collection of their probabilities. So this is the standard form, which is nice if it's just one host, but in our case, we have n hosts that are seeing a problem at the same time. So what we do is we drop the first n-1 terms. That's what actually gives us that probability of at least n hosts seeing a problem. So that allows us to estimate the union probability for that collection of hosts seeing an event at the same time. And just to give you an idea of what we gain by having multiple hosts corroborate each other, this is a graph of the relative likelihood of problems happening. We simulate a network. We assume that hosts are seeing a problem with a certain probability, slightly randomly distributed, which gives you these curves, and then see what's the relative likelihood compared to one host seeing an event with, in this case, 3, 5, 7, and 9 peers. And at a high level, what we see is that the more events see an event at the same time, the less likely it's happening. This is what just falls out of that equation I showed you. And another nice thing is that as you add more hosts that are seeing events, it's orders of magnitude difference in the likelihood. So this again confirms the intuition. It's unlikely that a lot of hosts see a problem at the same time just by coincidence.
So how do you compute this number? I'm trying. How do you? Don't you have to know the truth to compute this?
So we simulated a network. We said between 1 and 9 peers are in the same network with something like, there's a group of hosts, and they see problems. Yeah, this is not from the data. This is entirely analytic, just to show that this likelihood analysis has some weight behind it in terms of the corroboration, like what that buys you.
How do you, I think you get the answer, but I don't have it now. How do you think that, how do you compute the probability on a node having the problem?
That's done, it's always an estimate based on samples of what they've seen. So they sample their signals at a certain rate, and the number of times that they've sampled and looked for a problem becomes the denominator. And the number of times that they've seen them. Okay.
Now probability is the calculator.
Oh, okay. Sorry.
That's all right. I just thought I just got back to my first grade. Anyway, never mind. But the question I had is, so you've got these events that are happening, right?
Mm-hmm.
And you suddenly see some problem, for example, in throughput, for example,
Mm-hmm.
and it tells you might have a local problem. So how do you go from there to the probability part? You posted an event in your central storage system saying, hey, I'm seeing this thing, and I think this is my this is a medium average, whatever you had,
Mm-hmm.
and send it up there. So now how do you go from there to probability?
So each host publishes its local probability, which is, so there's all of these L sub h's is the local host probability of seeing an event. So they're all publishing this information. So when you go to the distributed store, you have access to all those values. I think this is, correct me if I'm not getting at your question.
So how do you calculate the local probability is what I'm saying? So it's sort of like, they're just looking at some events, right? They're looking at some threshold, some throughput fell down, for example.
Mm-hmm.
So how do you go from that to probability?
Well, that's what I was getting at before, is that at every time instance that there's a sample being done, you're maintaining a counter of the number of times there could have been an event detected, and then you also keep a separate counter for the number of times you actually detected a problem using those settings, and that's your detection rate, which we use as the probability.
Just like the moment you detect it, you start doing some active probing right away, get the answers, and actually have a better estimate that you actually have a problem, as opposed to just continuing the same form of just capturing data and then calculating the probabilities? It's
possible. There's always this tricky issue with active probing during a network problem that you could make it worse. So I would think that the first step here, because this is pretty lightweight, publishing this information, is getting access to that information, coming up with some idea that there's likely a problem, and then doing your controlled probing. Honestly, I think it's a really hard and interesting problem. Because then the host should probably coordinate with each other to make sure you don't want all of them doing the same probing. That's wasteful. And you're already in the middle of a network problem. So how much can hosts give you there is, I think, a really great question that I don't have an answer to right now. I think it's a really interesting area to look into. Okay.
So I'm actually interested in what the false positives, how many do you get because of this?
Yeah, false positives and negatives is another issue in this. Yeah. All right, well, we can go through this and come to that point when it comes up. So another thing is you can monitor multiple signals. I've alluded to this before, but in BitTorrent you have upload and download rates, which are somewhat independent of each other. And the more independent signals you have, the more confidence you can have in a local problem being real. So that was just another probability analysis. So given a union probability, now how do we actually determine whether something is coincidence or likely to be a network problem? And here we compare two probabilities. So we have a union probability, that's coincidence, and then empirically, the rate at which a collection of hosts in the network are seeing problems at the same time. And we compare those two values using a likelihood ratio. The empirical one is in the numerator, And if empirically this is happening more often than chance, we're saying that events that are being detected using these settings are likely due to the network. This is the empirical measure we have, as opposed to chance, which is the union probability. So anything greater than 1, that's like a very loose threshold. So we can empirically derive a stricter threshold. How much more likely than chance does it have to be before it's actually a problem that operators should look into? Another thing about this likelihood ratio threshold is you can use it as a tuning knob. So the higher the threshold is, the fewer alarms that are generated. Like any system, you could potentially have more false negatives that way, but it does just give you one value that you need to tune, sort of a master control switch on this system. Okay, so how does this work in that BT Yahoo network? And here in these graphs, there's 2 different detection settings, noisier ones on the top and stricter ones on the bottom. And this is the same timeline that we were looking at before for throughput, but now I'm plotting the likelihood ratio at each moment for events that were detected. And so the top one uses a deviation threshold in terms of the moving average of 1.5 times the standard deviation over the window, which is a pretty loose setting. It uses a pretty small window also, which means we get a lot of events that each host detects. And this is where you could potentially have a lot of false positives. But because they're detecting so often they're detecting problems, the union probability actually makes it pretty likely that the events happen by coincidence. So most of these fall below the threshold, and you say these aren't likely network events. We did get one spike at the end here. And this is something, if you look back at the performance graphs, when all the hosts recovered at the same time, well, they're essentially all their TCP timers and windows and everything are growing at the same rate, and then they reach their capacities and all back off at the same time. And it's something, so it was very synchronous, which is why it came out like this. A lot of hosts saw it at the same time, but it wasn't a very big event in terms of throughput, which is why you needed a noisier detection setting to see it, I guess a finer grain one. So the bottom one we use a stricter detection setting, and there's some nonlinearity when you increase the number of standard deviations you look at. There's actually quite a big difference in how much that throws out. So here you'll see throughout this entire window, when there's 0, that means hosts didn't detect any events. So you see they're not seeing very much, which is good, because the things that they do see are those 2 events that I showed you before. The one at 1054 that that first group of hosts saw, and then the other one that the rest of the hosts saw. So this is encouraging. There's a couple moving average settings that detected different things, but which one do you choose?
So both graphs show the same data?
It's the same data, just different moving average settings to detect things.
So why the events are so different?
Yeah, they seem... Right.
Why are they different?
So it seems like the choice of the parameters you make can completely change the picture, right? The first graph and the second graph are very different. I'm not talking just in terms of sort of one is jump here and one is straight. I'm talking about the events in one don't correspond to the events in the other.
Right, so different detection settings can detect different types of events. That's something that we found. So if you're looking for a big drop in performance, you use something that requires a bigger threshold deviation to trigger, and you can use a larger window size to account for more noise in the signal. If you're looking for maybe a smaller deviation in this sea of noise, you use the looser thresholds, but what you get in return is that every time you see one of these events anytime you see something above 0, hosts were publishing something to distributed storage, and that can increase your overhead. So there is a trade-off. So you can see if you're looking for something that looked like this back off after recovery, okay. I mean, so I'm not trying to say that we actually use these settings in practice. This was more of a case study to say that even if you use something that's noisy, because of the probability analysis, you can filter out the things that are bad. And what you'd really want to do is, so you use a collection of settings and then select the ones that are not generating an unreasonable amount of overhead in terms of reporting events all the time.
I see it as like, if you have some transient issues that you don't necessarily care about, and this will pick up, the upper setting sort of picks up all of those issues, and so they may or may not be interesting, but it's the big ones that are actually more interesting, because then you have to do something about it.
Yeah, and the transient ones, maybe you treat them differently. Maybe it isn't something you get an alert about all the time, but if enough of them happen and there's some cases of periodic events that are very hard to track down. And if that's something you're looking for, you know that there's periodic events that happen, and so you sort of wait for enough to accumulate, and then you can get an alarm.
How did you figure that was TCP?
Oh, we're guessing. We can't say for sure, but it happened around that time, and we know that all the hosts are using TCP for BitTorrent, and it certainly looked from the graphs like they all got the same recovery at the same time. So it was around that point when a bunch of hosts, they were going up, 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 and then went down.
The other thing I was thinking is that it would be interesting actually to know if the transients or these things are happening fairly regularly and quite frequently. Because that may not be good for TCP or things like that, right? When things go bad, and then so what is causing that? Why is the network not as smooth, for example? Sort of interesting.
Yeah, that's an interesting question. It's something that we haven't looked into, but it's definitely interesting. Okay. So that was the case study using BT Yahoo just to show you how this thing works. And so now I'm going to go into a wider area evaluation. I'm just going to give you some summaries of those results. But before I go into it, I have to give you some disclaimers. So ideally, I'd like to come up here and tell you the false positive and negative rate. That's what everybody wants to hear in a detection system. The simple fact is that I can't give you those numbers. And I mentioned this before. Almost no ISPs want to give you actual reports of all the problems that they saw. Even if they do, what they're looking for is not necessarily what we're looking for. I don't know what to do about that.
Call Henry. Henry, we need help. Okay,
I'll just keep going. So these ISPs, as I mentioned before, are we got a funny little thing there. I'll keep talking. Yeah, you do your thing. As I mentioned before, the ISPs have these in-network monitoring tools, and they're generally looking for major problems. We're at the end systems and looking for any problem that a collection event host sees. So we're really, in a lot of cases, looking for different things. And the bottom line is there's no ground truth, and this affects all research in this area. So what I can do is get reports of events from the sources that we have available to us, the public interfaces. And the example I'll use is the BT Yahoo network. We use a month of their data. And then we also worked under NDA with North American ISP, and they have a collection of event reports that we were able to use and run against our analysis. And so we can compare what we saw that was the same and what was different. Another limitation is, of course, this only works where the ISPs have coverage and where we have coverage. So in many cases, there will be events that our approach didn't detect. And most of the time, this is because while we have a lot of users, they're not necessarily all online at the same time in the same network. So we're limited just by what we were able to get out of our data set.
So do you have some graphs to sort of show after how many users do you need to get certain level of confidence in what you've detected?
I don't have those graphs in this talk. What we do is we enforce a minimum of 3 users, and then after that it depends on their event detection rate for that likelihood analysis. If there are 3 users with noisy signals, really noisy detection, they're not going to be very helpful. But there's an interplay between the number of users. And the closest thing I can do is go back to that analytic probability graph. And you can twiddle the numbers in there and see, given a certain event detection rate, how many users do you need in corroboration before you get something meaningful. OK, still have that lamp thing. All right, so I have a bunch of results. I'm going to focus on just 2 things here for the rest of this talk. In terms of coverage, we'll look at how many confirmed events we saw based on our data sources. In terms of efficiency, we're going to look at the event detection rate, which goes at the issue you brought up before, which is, are we generating alarms at a rate that would annoy operators? OK. So we looked at 1 month of data from BT Yahoo. What we found there is we detected 181 events over the course of a month. We found that 54 of them occurred during the confirmed problems on their website. So if you look at our little Venn diagram here, you'll see that about 2/3 of our events were not confirmed by them. And we captured most but not all of their 68 total events that they reported on their website. So it seemed like decent coverage. And at this point, you might ask, well, what are those other 120? And Some of them may be false positives, some of them aren't. The hard thing with this type of analysis is we did it offline. We couldn't interact with the operators at the time to see what was going on. But one of the takeaways here is even if these are all false positives, we're looking at about 4 events per day, which seems reasonable for an operator to have to deal with.
But 4 events a day, 3 of which are false positive.
Possibly.
Possibly, yeah, possibly.
Yeah. And what we found in our data is that a lot of these events are clustered in time. We try to group them, but there's certain thresholds we set for grouping them, and sometimes those don't even fit. So in some of these cases, when there's 4 events per day, it's not like the operator, it's not like every 6 hours they get a warning. So it's not, even then, it's not as bad as it may seem. Okay, so then for the large North American ISP, we had a different kind of data. They gave us the number of subscribers affected by each problem. And there's a very large database, and there's actually cases where there's like 1 subscriber that was affected by a problem. We can't detect that. That's not what we're designed for. Also, they had a large number of business users where BitTorrent is not commonly run. So with those caveats aside, we group the events according to the number of subscribers affected by the problem. And in this case, with more than 10,000 subscribers, we could confirm the events for half of them. We saw the exact same thing that they did in terms of our probability analysis. And then there was this 38% more. I told you I set a minimum threshold of 3 users, at least 3 users seeing a problem before we can say anything confident about it. In this case, we had 2. And if you look at the performance graphs, you see, oh, look, their throughput just went to 0 for a while, right around the time they said there was a problem. But we didn't have enough confidence to say it's confirmed. And then in the range of 10,000 or 1,000 to 10,000, we do a little worse, which is as expected. The fewer subscribers affected by a problem, the less likely we'll have users there in great enough numbers to detect them. So here, we actually didn't have enough users to detect any of them for sure, but we did have, for 2/3 of them, we had cases where there were 2 users seeing a problem at that time. It gives us some idea that we can detect these problems, but unfortunately not enough coverage.
Use NTP?
It does.
Okay, so you don't rely on the system's clock. You use
Right.
your own NTP thing. Okay.
Right, and for our offline analysis, actually, because they're reporting data to our centralized servers for the purpose of our offline analysis, we use the server clock as sort of a global time, and so there's that issue. But in the deployment, we had to use NTP, so they all do that in the deployment.
So, no, I guess what I'm saying is, it's likely it's not a time issue.
Right. Yeah. These. I mean, if you look at the performance graphs, though, in the case of an outage, there may be misalignment in the drops to 0 just because hosts will occasionally have to drop data because it doesn't get back to us. But it's usually not a time issue. We can get usually within a couple minutes of what it should be. And if we see clocks that are so bad that we can't determine anything meaningful about when their data actually was recorded, we throw that data away in the offline analysis. But yeah, clocks are horribly unreliable, as we found.
We're trying to determine whether we should try to fix this, or so that'll depend on how many slides you have. If you have then we fix it. If not, then we'll
there's like 5 or 6 slides left. I'll be done pretty soon.
Sorry about that.
All right, no problem.
Get rid of it.
It's okay. If you guys are okay. It seems to be fitting between a lot of the text, so I think we're good. All right, so the other thing I'm going to present is the event detection rates. And here, I want to come back to that point about the likelihood ratio, using that as a tuning knob. So what I plot here is the CDF of the likelihood ratio. This is the tuning knob value. And I put in this gray box area. It starts at a threshold of 2. And so the CDF is in this case, the percent of the time that network problems are detected at a certain likelihood ratio. So what we're seeing over here is at a ratio of 2, there's, in this case, 98% of the time there's no events are seen. So only 2% of the time network operators would see events, which seems like a reasonably small amount. And this is using the noisy detection settings. So maybe that's still too much. what you could do, you can see you can start sliding this threshold, and of course the curves get closer to the top of the graph, which means they see fewer events. So that's what we mean by using it as a tuning knob. So even for each different detection setting, you could have a separate likelihood ratio, if that's it. Exactly. It's the size of the window and the deviation threshold. Those are the two key parameters. And then it's a slightly different graph for using those the other detection settings, the less sensitive ones. Here, less than 1% of the time, with a likelihood ratio of 2, operators would see events. And there's, you see after a while, as you go beyond 2, you just get nothing. So in this case already, they're pretty rare events, which seems reasonable for operators to use this system. They're going to get several events per day, but it's not going to be tens or hundreds. S is the number of signals that are used to monitor. Sorry, I should have pointed that out. So in this case, these are different. They're upload rates, download rates, and then we also look at the per connection upload and download rates as potential indicators of network problems. And they're correlated but somewhat independent, and as you add more of them, you just get more potential corroboration. And that's why you see the ones with the ones with more signals are rare. It's very rare that all of these things happen at the same time. Okay, so this is a real system. It's been deployed. It's actually over 45,000 users now. This is implemented in just over 1,000 lines of code for the core detection. This is one of the advantages of moving averages, is they're pretty easy to implement. That said, there's still thousands and thousands of lines of code that have nothing to do with event detection. You have to have a user interface so users can see what's going on. It has to interact with the DHT. There's a lot of other stuff that goes on here. That said, in terms of event detection, our implementation currently samples throughput every 15 seconds. It could be done more often. Right now we find this is good enough, a 15-second granularity in terms of detecting problems. So we look at transfer rates. We do look at the torrent state, pretty much all the same information that we have accessible offline through our ONO data collection. And it publishes its information of the built-in DHT. And in terms of how we group hosts, we use publicly available information already gathered by views. And this is BGP prefixes and ASNs. So hosts in those two types of network groupings, they can localize that way. We are looking at other ways. I've used offline some whois information to isolate hosts of the same, like BRAS, for example, but that's a little trickier because you have to do text parsing. These are at least easy to work with. And then another part of our system, as I mentioned before, news site. So I mentioned one of the problems is that ground truth is hard to come by, and we would like to actually have more information about network events when they happen so that we have more data to compare our approach against and compare alternative approaches against. Towards that goal, we've taken the information that we make available through a DHT, and we publish it on this website via this Flash animation. Anybody can check this stuff out. We're still kind of beta testing it with operators. We need to figure out exactly what kind of information they need. And so to make it more useful, they would actually register for alerts, and then they can be notified when problems occur in their network. But the high-level idea is that they have this interface that can go and actually confirm them. And just as an aside, in terms of why operators would want to do this, since I just told you that it's something that they don't want to share, is that you do see on mailing lists like Nanog that operators do share these problems with each other to diagnose cross-network events. And that's one area where our approach can detect these problems, and they would want to actually make that information available. So we hope that this is something that will eventually catch on once we get it further developed. And just to step back for a slide, I just want to put this work in context of a larger umbrella project, which is 3R. So this is like the whole green theme, reduce, reuse, recycle, in this case for network measurements. So you reduce the amount of network measurements you have to do by reusing existing measurements or recycling them. So reuse, if you have a measurement that's exactly what you wanted, you just reuse that data. Recycle, well, you saw what we did here in terms of using BitTorrent to actually monitor the network, doing something it wasn't intended for. So there's lots of advantages in terms of scalability, in terms of just design. but these open questions have always been, how good are these users, how good is the take of on the network from reused or recycled information that you don't actually on-demand measure. And we've shown that it is good enough for a number of different projects. We use CDNs to identify nearby hosts. We've used this also for network positioning, and of course I just talked about how we do network monitoring using recycled information. All right, so this is the end of my talk. In summary, we crowdsourced network monitoring through and developed a prototype that we call News. It uses BitTorrent to detect network problems. We also put out News Site, a public interface for viewing these and potentially eventually labeling network problems. There's still a number of open issues. It would be great to explore other types of network groupings toward this goal of network diagnosis. After you detect that there's a problem, actually further isolating it. It'd be great to have more ground truth, as I said. And then back to that point you raised before is, how does this work with other applications? So it seems like there's opportunities in VoIP or video streaming, just a number of different applications, and then see how they interact. So these are all open issues that we'd like to look into. And that's it.
Just to sort of follow up on what I said, the reason I said that is because when you look at this whole network diagnosis problem from the enterprise perspective, right?
Mm-hmm.
So as you were speaking, I was thinking, what is the dominant application that, let's say, we could instrument to find faults in the network? And I'm not so sure. I mean, the one only I think that we exchange. Yeah. Yeah, we'll do that or something. So, but there, I mean, you're familiar with the Sherlock work that we did, right?
Mm-hmm.
So there we sort of just took the approach of, it was an operating system approach where we sort of created, over a period of time, we created how the application was responding, how the network events were happening, how fast, and so we drew a distribution out of it. Mm-hmm. So anytime in the future when things would not fall in that part of the distribution, that was the trigger mechanism for us. So it didn't actually assume any state information about the application. It just looked at the I/O from the application and looked at that.
Right. And it's a very complementary approach. So
anyway, that's where I was coming from when I asked those questions.
Yeah.
Sorry, I was late, but I'm all those likelihood analysis is fantastic. But I'm from a network monitoring group.
Mm-hmm.
It's kind of more interested in how we are thinking about distributed collect data, but we are analyzed on the protocol interaction kind of problem. So my question is, you have agent-based, all the hosts have an agent installed, and you collect from there, or
his application, he has plugins to the application itself. So the application complains. There's no separate agent.
So on each host, each application have a report this.
Yeah.
In this current prototype. Yeah.
Think of it like as if you install a plugin for IE. I see, right? So IE is the application. You cannot, he created a plugin. You just install this plugin, and it does all of this. I see. But I understand.
So the protocol underneath there, transport the events is all like a UDP or kind of packet. How the scale works.
In terms of the publishing the local problems that each host sees, that is done through, in our implementation, a distributed hash table. And they're small reports, about 40 bytes in our current implementation. So, so I think it fits nicely with the DHT, which is meant to store key and generally small values in terms of BitTorrent. It doesn't have to be a DHT. We just need some kind of distributed storage that all hosts can get access to.
So you guys can go to up 554K host reported to the same one server.
Well, 45K hosts in our current implementation, they use the DHT. So it's actually, I mean, for offline analysis, they don't have to do this. Some of them opt out of reporting data, but we do collect them in a centralized server. 45K is easy for that. But as you scale this out to millions, I can tell you just recording from the subset of our ONO users that report data, that gets tricky. So that's why we want to avoid any centralization, any reliance on centralized infrastructure.
So those are in a security issue. Is there any security issue when you send the events? We don't really care about what content in there, right?
Right, in terms of privacy?
Yeah.
Maybe we should take this offline because you're asking the questions you actually covered already.
Oh, I see. That's why I was.
I have one comment before I have to leave now, is that, so, you know, one of the, so when you sort of take it to the next step, which is you want to do some root cause analysis, and you know, there you sort of start to say, okay, it's not just the fact that something went wrong, I want to see what went wrong, right? Then instrumenting one application may not cut it.
True.
Because, I mean, if you have, you know, lots of services inside the network, and a particular application will only stress test those services, another service may cause the problem to happen, and if you go down that path, then you will miss that completely. So you actually want not just broad coverage from the application running on many monitors, but also many applications testing all the different components inside the network.
No, I completely agree, and I guess in my view, when you move to the domain of active probing, that includes being able to simulate other protocols or other applications, and I agree, you definitely want to see those kinds of
It's not necessarily about active probing, it's just about coverage.
Okay.
The network coverage, I mean, active probing is yet another technique that you would apply, but if you, what I'm saying is if you don't even see a particular service in the path of the application that you're doing, you are not, so probing wouldn't make
the perfect example for this is you have probably very little visibility in enterprise networks.
That's
just by
true.
the nature of BitTorrent being,
Exactly. Although it's funny, there's some. There shouldn't be, but there is. We've even seen it, I mean, people use this over 3G, so it's like, why are we seeing the AS number for AT&T Mobility? It's like, oh, wow, okay, they're doing BitTorrent over 3G. But people have their laptop cards, so, you know, they don't really think about that.
Well, okay, thank you.
All right, thank you guys.
Feel free to actually, we can discuss some of your questions.